Good morning to all of you. Today I will start my lecture number 6. See, in the previous lecture what we have done theorem 1.2.2, that is theorem 1.2.2. That is, if A is an element of a semigroup, so I am recalling this, A an element of a semigroup S, then there are the two cases. Case 1, when powers of A are distinct. So in this case, we get a monogenic subsemigroup generated by an element A of semigroup S. That is what we will get: infinite semigroup. A square, A cube, A to the power 4 dot so on, and this semigroup is isomorphic to set of natural numbers with respect to addition. So if power of A are distinct, then we will get this. In case 2, we have seen that when repetition of powers of A do take place. So in this case, what we have seen that we get homogenic subsemigroup generated by an element A, which is equal to A square dot so on A to the power m, A to the power m plus 1 dot so on A to the power m plus r minus 1. Correct? So what is the order of A? Order of A also I have defined. Order of A is the number of elements in the monogenic subsemigroup generated by an element A, that is equal to m plus r minus 1. And what is m, what is r? I told this that m is what? Index. R is what? Period. So we also prove this, that A to the power m is equal to A to the power m plus r. In previous lecture, by mistake, I wrote A to the power m, A to the power r is equal to A to the power m plus r at some place. So one student bring it to my notice that I have written this. So it was wrong. It was wrongly written. Basically, the fact is that A to the power m is equal to A to the power m plus r. So always try to see the board with mathematical eye. If by mistake, by human error, it may be possible that, for example, if I write 2 plus 2 is equal to 5, then all of you, nobody will copy this, because we have mathematical sense. We will correct itself, that is 2 plus 2 is equal to 4. We will not copy this. So such kind of, if mistakes are done by teacher, then the student must improve this and also bring it to the notice of the teacher, so that he can do correct. He can do the correct way. So the fact is that A to the power m is equal to A to the power r. This was wrong. Anyway, so we have proved this thing, that A to the power m is equal to A to the power m plus r, and this is the monogenic subsemigroup. And also we have proved that Ka A to the power m, A to the power m plus 1 dot so on A to the power m plus r minus 1 is cyclic subgroup of monogenic subsemigroup generated by an element A. This is what? This is cyclic, and this is cyclic, and it is generated by which element? A to the power m plus g. Generator is what? A to the power m plus g. And what is g? G, that is m plus g congruent 1 modulo r. So in this way we can find out the g. So K is this is what? K is what? Cyclic subgroup. It is subgroup of A. So these facts we have proved so far, and also we have since K is a group, we also find out the identity of the group of this group. What is the identity? Identity is that is A to the power m plus z this is the identity where is identity of KA. And what is Z? M plus Z is congruent to 0 modulo R. So in this way, A ki power M plus Z is the identity. Basically, A ki power M plus Z is the idempotent in this group. And all of you know that in a group, idempotent is the only idempotent is the identity element of the group. So if we able to find out the idempotent in a group, then same will be the identity of the group, correct? So A ki power M plus Z is the identity of this group K, and M, how we find out Z? It is such that like M plus Z is congruent to 0 modulo R. So these are the things. So we have proved this. Now I will give the example of that. That is, for example, if you consider set X is from 1, 2, 3, 4, 5, 6, 7. Correct? Now, this is full transformation semigroup. Full transformation semigroup. That is, it consists of elements. It consists of all elements from X to X. F is what? F is function from X to X. Now we consider an element alpha. Alpha, that is, we write like this: 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7, 5. 2, 3, 4, 5, 6, 7, 5. So naturally, this belongs to tau x, full transformation semigroup, because it is alpha as permutation, correct? 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes to 6, 6 goes to 7, 7 goes to 5. Basically, all permutation mappings are from X to X, and also they are from 1 on 2. So basically, all permutations on X are the members of this full transformation semigroup, correct? So I have taken this element from the tau x. Now we find out the monogenic subsemigroup generated by an element alpha, correct? So to see this, you just see, you have to find this, correct? You have to find this. You have to find this that it is generated by generator of K alpha. Generator of K alpha. You have to find this. You have to find the identity of K alpha. So to find out this, what you have to find out? First thing is to understand the problem. So what things you have to find out? You have to find out the monogenic subsemigroup generated by an element alpha of tau x, correct? To find out this, you have to find out the index as well as period of alpha. If you find out the index and period of alpha, you can find out easily what is this. What is the set? Monogenic subsemigroup generated by an element alpha. After that, you can find out what is K alpha, and to find and also you can find out the, once you find out the K alpha, you can find out the generator of K alpha as well as identity of K alpha. So first of all, we have to find out the index and period of this element alpha, correct? So for this, what we do, just find out the powers of alpha. You see, this, this is permutation. This is permutation. Now you can calculate alpha square, alpha cube, alpha 4 dots. One you can calculate. Now you see that you will see that you calculate this alpha 5, alpha 6, alpha 7. You can calculate all these powers, and now you see, you can check that. One can verify that. We verify that. We can verify that alpha की power 4 is equal to alpha की power 7. When you calculate alpha की power 4, when you calculate alpha की power 7, you see that both will be equal to each other. Alpha की power 4 is equal to alpha की power 7. Now, what you can write alpha की power 7 like this: alpha की power 4 plus 3. It means that alpha की power 4 is equal to alpha की power 4 plus 3. It represents what? It represents C. A की power m is equal to a की power m plus r. It means what? M is equal to 4, r is equal to 3. So it implies what? Basically, it implies that index of alpha is 4 and period of alpha is 3. So we have find out the index of alpha and period of alpha. Now it is not difficult to find out this one. What will be this? It will start from where? What will be the order of alpha? We can find out m plus r minus 1. That is 4 plus 3. That is minus 1. It means what? 6. So it will start from alpha square, alpha cube, alpha 4, alpha 5, alpha 6. Isn't it? So this is alpha. And now, what is the generator of K alpha? What is K alpha? K alpha you can find out very easily. But it will start from here, alpha. You see this a की power m plus 1 rods on a की power m plus r minus 1. A की power m is what? M is what? 4. So it will start from alpha power 4, alpha 5, alpha 6, alpha की power 6. So this is K alpha, correct? Now we have to find out the generator of K alpha. We have to find out the identity of K alpha. So see how we find out. You can see that since 4 is congruent to 1 modulo 3, therefore alpha की power 4 is the generator of K alpha. Correct? You can see that 4 is congruent to 1 modulo 3. It's obvious. So now, see, you want this m plus g is congruent to 1 modulo r. You are looking about same m plus g, which is congruent to 1 modulo r. Then what? A की power m plus g is the generator. So now here 4 is congruent to 1 modulo 3, isn't it? Because period is 4. R, in the place of r we have 3. So alpha की power 4 is the generator of K alpha. And also you can verify that every element. You can see that from here alpha की power 4, and you can see that if you square if you take alpha की power 4 square, if you alpha की 4 की power cube, you can verify by yourself alpha की 4 की power 5, alpha की power 8. You see that it will come equal to alpha की power 5. And now alpha की power 4 की power cube, that is alpha की power 12. If you calculate it, you will see that you will get alpha की power 6. So in this way, you can say that it is generated by an element alpha की power 4. So alpha की power 4 is the generator of K alpha. Now, what is the identity of? Now you can see, since 6 is congruent to 0 modulo 3, therefore alpha की power 6 is the identity, or you can say idempotent element of K. So alpha की power 6 is the identity of K. Isn't it? Also, we can draw the table, K table. because we have to find out m plus z, which is congruent to 0 modulo r. So here 6 is congruent to 0 modulo 3, so 6 is of our use. That is alpha to power 6 is the identity of k alpha. So in this way we can find out the table k alpha. Alpha to power 4, alpha to power 5, alpha to power 6, alpha to power 4, alpha to power 5, alpha to power 6. So it will be alpha to power 5, alpha to power 6, alpha to power 4, alpha to power 6, alpha to power 4, alpha to power 5, alpha to power 4, alpha to power 5, alpha to power 6. So this is the Taylor table, binary operation table of Taylor table for k alpha. So we can check that k alpha is a cyclic subgroup of this monogenic subsemigroup generated by an element alpha. This is the example, supporting example of the previous theorem 1.2.2. Now we move to next fact. You can say A is common if and only if A and B have same index and period, have the same index and period. Therefore, let A and B are the elements of finite order in semigroups. Let A and B be elements of finite order in same or different semigroups. Then now see what is the problem. Let A and B be the elements of finite order in same or different semigroups. Then what we have to prove? We have to prove that if these two monogenic subsemigroups are isomorphic to each other, it implies A and B have same index and period. We have to prove this. So we have to go in both ways. That is, first we assume, for example, if we assume, we have to see both cases, that if these two monogenic semigroups are isomorphic to each other, then we have to prove that A and B have the same index and period. Conversely, so that assume that A and B have the same index and period, then we have to prove that these two subsemigroups are isomorphic to each other. So we have to done in both ways. Now let's see. Let A and B have the same index and period. Then A is what? A square, A cube, or so on, A to the power m plus r minus 1. You say index, say m and r. Say m and r like this. Okay? No doubt that once elements have finite order, then we have the second case, that is the monogenic subsemigroup is not infinite. It will be equal to some A square dot so on A to the power m, A to the power m plus 1 dot so on A to the power m plus r minus 1. because the order of the element is finite. When the order of element is finite, it means order of, for example, A is the element, and we are saying element of order of A is finite. It means that order of monogenic subsemigroup generated by an element is finite. That is order of this will be finite. So it must have, A must have index, A must have some period. Then an order will be like this, m plus r minus 1 will be the order of an element A as well as the order of this semigroup. So then this now B will be like this, B square, B cube, or so on, B power m plus r minus 1. Now what we have to prove? We have to prove that these two semigroups are isomorphic to each other. So define a map in between them. We have to show that to prove any two semigroups are isomorphic, we have to prove that there exists at least one isomorphic map between them. So first we define a map between these two semigroups, and we show that this map is well defined. This map is morphism, that is homomorphism 1, 1 and on to. To define map. To define a map, say f from A to B by f of A to power L is equal to B to power L. Like this we define a map. Of course, you can see that this map is well defined. F is well defined, and also F is 1, 1. You can see F from any A to power L1 comma A to power L2 belongs to A. You can see that right over here. So A to power L1 is equal to A to power L2. It implies and implies L1 is equal to L2. It implies and implies that B to power L1 is equal to B to power L2. It implies and implies that f of A to power L1 is equal to f of A to power L2, which implies that f is well defined